And bonjour from Times Square. Bruno and Darko show here talking about AI, Biostat, etc. Hey, Darko, welcome to Times Square.
Amazing to see Times Square, and it actually reminds me of movie Blade Runner. I was watching a few days ago. I've never been to New York, so it's really amazing to actually have some experience from you there. So thank you so much for having me, Bruno, and looking forward to discussing AI, biostats, etc.
Well, today we thought we'll talk just about essentially what does Times Square evoke or inspire us about AI and biostats? Is there any topic, any concept that comes with it? So we'll go to that in a moment. But I wanted to talk about the Blade Runner for a second. So, did you just saw the new one or the old one, the Blade Runner movie?
Yeah, the new one.
The new one. Okay.
I'm a big fan of the old one as well, but I watched the new one. Actually, I watched it 5 or 6 times ago.
Oh wow! Wow.
5 or 6 times. In some.
So here's a question. Yes, where are the flying cars? Right. Certainly by now we should have had all the flying cars in the world, and they did not happen. Now with the drones, it seems that they're going to become safe enough and energy efficient enough. The problem is going to be noise. I think that flying cars is not going to happen, unfortunately, because there's no way to make them non-noisy. And even if they're super safe, the noise level, just because of having to, lift in the air, you cannot do that without being noisy. So we'll see. That's my prediction, unfortunately, that flying cars are surprisingly not going to be truly part of our future. Hopefully I'm wrong. So New York City, center of the world for some people, and Times Square, center of New York City. I used to live in New York, and a special place for me. Also, LARVOL has a billboard over there that we rent every month or so. We'll have it with our content in a couple of days, and we highlight key opinion leaders in cancer and other things and advocates. So it's a special place for me and for all of us. And what we thought is that we'll talk today about the link between what's happening in Times Square, whether it's the crowd, the random walking in some ways, and AI, biostatistics. So we don't have a very specific agenda today, but what is in your mind, Darko, to start with?
I think we could actually randomly connect to what you're doing right now, which is randomly walking in a beautiful New York City. So maybe we can connect that to how important the random walks are in AI, and specifically, since we are also working on a number of projects in that field, the use of random walks in knowledge graphs. Now, we know how important the knowledge graphs have become in AI. They are now at the frontier of developing memory, knowledge, and predictive models for AI. So maybe we could discuss that. How important are the random walks there, and how can we apply them to the knowledge graph? Yeah. What do you think, Bruno?
I love it. By the way, I love to random walk, not in a statistical sense of the word, but in a city. I love to just walk without a specific aim and just explore the city I'm in. This is one of my pleasure in cities I know and cities I don't know, whether it's in Paris or in New York. By the way, you know that already, but or you don't. But at the top of this center of Times Square, there is where the ball drops at midnight, and the ball is not there yet, but it will be above the 2025 over there, which I assume is going to shine through 2026. So there you have it. So random walking, in particular in the field of knowledge graph, right?
Yeah, I think that would be very, very interesting topic.
Okay. Well, actually, and usually in this conversation, I play the role of the guy who doesn't know too much, and you educate me. Right? So, what is a random walk in the field of knowledge graph, and how does it help us?
Yeah, so the random walk is really a statistical technique, right? So it's been there for decades, used in many statistical approaches where we essentially try different paths randomly and then try to gain something from this. Now, in the sense of knowledge graphs, uh, because knowledge graphs are they are composed uh, from nodes and edges, right? So they're a graphical structural representation of nodes, and these nodes could be anything. They could be words, tokens, variables in oncology, for example, and then the edges would be connections between these nodes, their relations. So how can we use a random walk there, and why it's super important actually in the field of AI? Random walks can, let's say we start at a specific node, uh, and then we try to randomly uh, form a connection or jump to some neighboring node. And then we repeat this process. So we randomly try to relate to nodes in the graph. And you may be asking yourself, like, what do we achieve with this? Well, it's super interesting because when we randomly jump from node to node in a graph, we can actually discover some patterns, some hidden patterns. Let's say, we have two nodes in a graph, and one node is the treatment effect, and the other node is a specific disease. So if we randomly jump through the graph, and we suddenly discover a pattern, a connection between a specific drug and a specific disease we didn't know about before, because they appear frequently in that random walking. We can say, well, they appear frequently, there might be some connection there. So that's just one example how random walking through the graph, as you are now randomly walking through the New York City, can actually help us discover some patterns that we didn't know about before. How about that?
And so here's what I don't understand. In a knowledge graph, when you want to do a GNN, the graph neural network, you want to borrow some knowledge, some patterns from one graph to the other. I understand it. I understand that. But what the advantage of random walking the graph versus systematically, I guess, going one node or two nodes beyond where you are? Is it just that you cannot go through all the nodes, so you might as well randomly pick a few? Maybe that's as simple as that. Is that you're sampling the nodes around you as opposed to going to each of them?
That's exactly one of the points. So instead of being biased towards what we already have in the data, by introducing a random walk, we are now sampling, right? We're trying to introduce randomness. And this randomness allows us to discover new things. So that's one of the advantages of graph neural networks, is that we can use them to discover new connections and new nodes. And as you said before, we can borrow information from one graph to another.
Okay, got
None
it.
of this would be possible if we didn't use some technique to jump from node to node and discover the structure, the whole structure
Right.
of the
Because
network.
otherwise, you would have had to be systematic and go to every node, and it would have exploded in terms of combinatorial possibilities, right? And it would not be computationally feasible. I think I understand now. Unfortunately, that kills the mystery of what a random. I thought it was something more special, Darko. Now I think, oh, it's just random sampling. So now the poetic, unfortunately for me, the poetic value of random walking is a little gone, but that's okay. That's fine. So I think maybe there's more to the story, but at least I understand. I understand the concept now clearly. So I understand, right? It's just random sampling of the nodes around you in a sequential way, so that you don't need to take the value from every node as you you learn the patterns of the graph as an AI. Can I say that?
I mean, yeah, that's one of the advantages, right? So we use the sampling to just make the process more efficient. That's one of the advantages. However, there is another very important advantage there, which is that when using random walks, we can actually try to predict, and that has to do with something that's called a world model for our audience, world model in AI. So sometimes we just need to predict how the world around us will behave. Now, speaking about the knowledge graph, we can use this sampling and probability. Eventually, from this sampling, we go to probability. We create a probabilistic model. And all of a sudden, we can predict what's going to happen next. And it's interesting that the transformers, which are so popular today in large language models, they actually work on a similar principle, very similar principle to the random walks, right? So the attention mechanism that everybody is speaking about, mathematically speaking, it's very similar to starting with a random walk and then figuring out which words are associated with other words in the text, right? So I think there's a very interesting parallel between graphs, knowledge graphs, and transformers regarding the random walks.
So I've got another question for you. Thank you for that explanation. So I would love at LARVOL to use knowledge graphs. And we haven't fully used it yet, in part because of a concern that we had, that our team had, which is that knowledge graph require more data than other AI methods. And of course, we're here in a very special place where there's so many people. So it makes me think, so are we limited because of that? And is there any rule of thumb about when knowledge graph makes sense and where they don't?
Yeah, I think that's a very good question. Knowledge graphs are, I think, very good for biomedical data because biomedical data is full of structural relationships. Even if you go and look at the biochemical pathways in human organism, you will essentially see these graphs of association of molecules, right? So I think knowledge graphs are great, but it's also important that to understand that, because knowledge graphs can become very complex because of all of these nodes and edges growing exponentially. And by the way, one node can be connected to 1,000 other nodes, right? So, the data requirement to make all these predictions in a knowledge graph accurate grow exponentially, right? And that means that we usually need to have enough data. We need to have a lot of data. Now, the rule of the thumb, there isn't one strict rule of the thumb. However, what experience tells us is that we need to have at least 5 to 10,000 samples at a minimum in a field such as oncology. But that's really a minimum, right? We would need much more if we want to achieve some state-of-the-art accuracy.
So we're going to be at the end of that short podcast in a second. And thank you for all of these explanations, Darko. I want to make a point that is not related directly to biostatistics and AI. So this billboard behind me, above the Pelé shop, is where we have our display. That's the billboard we rent. And Shahir Sheikh, our executive producer, hi Shahir, is the one who are organizing this event once a month or 2 months. We actually have some content in Times Square for LARVOL, which is always fun. Usually I try to be here at that time, and so I can take a picture or video as I'm in Times Square. So any final words on your side as we close this a little bit unusual podcast today, live from Times Square, New York.
I really want to say that I enjoyed the randomness of the podcast and an amazing random walk through a futuristic city of New York. Now, to tell you honestly, I'm a super big fan of movies like Blade Runner and cyberpunk games. So really, while we were speaking about this super interesting topic, I was also enjoying a tour of New York with you. So thank you so
We
much for that.
I don't, we probably both got a little distracted here, and hopefully the audience like the walk through New York. Thank you very much. We'll see you next week. Au revoir.
Thank you so much. Au revoir.